Welcome all. So today we'll start our section. Today we'll look into the analysis and design methods, okay. And today we'll be dealing with the pressure impulse diagrams and their applications in the blast and impact engineering. So to start with, what is a pressure impulse diagram? Okay. Pressure impulse diagram is basically a graphical representation of combination of peak pressure and the impulse producing the same damage level to a structural component. As we have seen in the Friedlander's profile, okay, normally what we were doing is that we were representing the blast wave with a Friedlander's profile. Okay. So normally we are dealing with the incident pressure. Okay. This is that positive time. Okay. So this was the positive phase and this was the negative phase and this was the time negative. Okay. And the sum total of this area was the positive impulse duration and this area was giving me the negative impulse duration. Okay. So the same feature. Okay. Now what we are going to do is that we are going to represent the pressure on one of the axis. Okay. Let us say on the y axis, and this impulse quantity we are going to represent on the x axis. Okay. So this is called the pressure impulse diagram. Okay. So it is basically a combination of the pressure quantity and the impulse quantity. Okay. And for each quantity it will produce the same damage level because the event considered is the same. Okay. This is also called an iso damage curve. Okay. And it is built for a unique combination of load acting on a specific structure and for a specific damage level and any type of failure. Okay. So here we see on this axis, y axis, we are representing with pressure, and on the x axis we are representing with the impulse. Okay. So now what we have done is that we have broken this thing down into different zones. Okay. So here, okay, so we are representing it with different curves, okay, with varying intensity of damage. Okay. So if we move from here to here, the intensity of the damage increases. So the green curve is low damage curve, red one is the medium damage curve, and the black one is the collapse curve. Okay. And then we have broken it down into different zones. Okay. This zones we are calling it as the impulsive zone, here we are calling it as the dynamic loading, and here we are calling it as the quasi static loading. Okay. So this PI diagram, okay, the pressure impulse diagrams are widely used for preliminary assessment and design of structures under blast loading. Okay. So they are normally applied to a single element. Okay. So they are normally applied to a beam element, wall element, or a plate element. Okay. And they are built up for a specific geometry, material, damage level and failure mode. Okay. And then what it does is that it divides the space into safe and failure zone. If the intensity is below the green line, we call it as the safe zone. If it is above the black line, we call it as the failure zone. Okay. So here we are showing a typical pressure impulse diagram. Okay. Moving ahead. So impulse. So impulse, as we have seen, we have the positive phase impulse. Okay. So this area we were calling it as the positive impulse phase. Okay. So this area. Okay. So impulse in the integral of the pressure over time. Okay. So basically the area under this curve. And since this is the integration of the area over time, it accounts for the intensity. Okay. That is the magnitude of the loading and the duration of loading. Okay. So this area, the sum total area, has the signature of both the components. Okay. So from this is the definition of the impulse. Okay. The shape of the pressure impulse diagram. Okay. The shape of the pressure impulse diagram resembles a rectangular hyperbola. Okay. So it has a vertical asymptote. Okay. So the vertical asymptote is impulsive regime. Okay. Short duration, high pressure. Okay. Then there is a curved middle. Okay. So this one is the vertical asymptote. Okay. So it represents the short duration, high pressure regime. Okay. There is a curved middle. Okay. So there is a dynamic regime. Okay. This is the transitional regime. Okay. And then there is an horizontal asymptote. Okay. So it has a low duration, low pressure regime. Okay. So this one we can categorize it as the quasi static region. Okay. So these are the three main regions of a pressure impulse diagram. Okay. Okay. So this is the typical response domain. Okay. So if this is the load function and then this is the response history. Okay. This is the loading function, okay, and this is the response history of the system, and for the different types of load functions we are representing the response history of the system. Okay. So, the first one we are calling it as an impulsive region, okay, short duration, high magnitude of the loading. Okay. So, this is how the response of the system will look like. Okay. Middle one is the quasi static, okay, the loading time is large, okay, and the pressure is also large. So, the total intensity is medium. Okay. So, this is the resistance function. Third one is the dynamic, okay, intermediate time and intermediate pressure. Okay. Okay. So, the characteristics of the diagram, it has a vertical asymptote, there is a vertical asymptote in the PI diagram. Okay. The load duration is less than the natural period. Okay. The loading time of the structure is very much less than the natural period of the system. Normally, the natural period of a typical system will lie in maybe say 5 to 30 hertz, okay, and here the loading will occur in milliseconds. Okay. The structure is still moving when the load ends. Okay. So, the loading has ended, okay, the loading has ended, okay, and the structural response has either just begun or it is continuing. Okay. So, this is governed by the short duration high intensity loads. Okay. The meaning of this, if you look into the previous graph, we see that the loading has ended, okay, but the structure has just started to move and it is about to reach its maxima well before the loading has ended. Okay. In some cases, in case of dynamic loading also, the loading has ended, but the structural response is still undergoing. Okay. This is governed by a short duration high intensity loading. Okay. The impulsive loads hit fast and ends before the structure react fully. Okay. This is the case. Okay. This is a typical case of an impulsive loading where the loading hit the structure very fast and it ends before the structure starts to respond. Okay. So, this is what happens in a blast event, okay, specifically the near blast events. Okay. So, this was the characteristic of the impulsive domain. Okay. Now, the characteristics of the dynamic domain. Okay. So, in the dynamic domain there is a transition zone between the impulsive and the quasi static regimes. Okay. Load duration is more or less comparable to the natural period. Okay. Maximum response occurs near the end of the loading. Okay. Most real world blast cases for building falls here. Okay. Neither purely impulsive nor purely static. Okay. So, most of the blast cases, okay, which are not far field event, which are not near field event, maybe the far field events fall into this dynamic range. Okay. So, here we can again see the dynamic range. Okay. So, the time, both the times are comparable. The structure will attain its maximum response just when the loading is about to end. Okay. So, this is the characteristics of the dynamic event. Okay. And most far field events, okay, blast type of events are characterized by this transition zone. Okay. This is the characteristic of a near field event. Okay. So, near field blast, impulsive domain, far field blast, dynamic domain. Okay. Quasi static domain. Okay. So, this is a horizontal asymptote. Okay. So, this is represented by the horizontal asymptote in the PI diagram. Okay. So, the load duration is much longer than the structural natural period and the peak occurs well before the load ends. Okay. The load behaves like a static force. Okay. Like it means that there is no significant dynamic amplification. Okay. And the peak displacement is reached quickly and sustained. Okay. So, here if you see, okay, the loading is continuing. Okay. The structural response has already started and it has saturated. Okay. So, the loading period is more than the structural response. The structural response normally attains well before the loading ends and it reaches an asymptotic level. Okay. There is no significant dynamic amplification here. Okay. So, this is we are considering as the quasi static loading. Okay. Near field loading for the impulsive part, far field loading for the dynamic part and quasi static loading. Okay. Quasi static loading here. Okay. So, from the response spectra to the PI diagram. Okay. So, when we have a typical response spectrum for an undamped purely perfectly elastic single degree freedom system under suddenly applied loads. Okay. So, we have constructed a response spectrum for an undamped, the system damping is 0 and it is a perfectly elastic single degree of freedom system under suddenly applied load. Okay. So, X max is the maximum dynamic displacement. Okay. So, here we can write the X max, K is the spring stiffness, okay. P naught is the peak force, M is the lumped mass, Td is the load pulse duration and T is the natural period of the system. Okay. So, here also we can see the curve for a dynamic zone, okay, the impulsive load asymptote curves and the quasi static curves. Okay. So, here this is X max and this is the ratio of Td over T. Okay. So, this is Td, this is T, okay. This is X max, K is the string stiffness, P naught is the force, okay, and M is the lumped mass. Okay. M will be used in order to calculate my T. Okay. So, omega equals to root over K over M. Okay. So, for different type of regime, okay, for the impulsive domain, dynamic domain, okay, we can create the response spectrum, okay, and this is the response spectrum. So, as we go in the course, we will see how to construct this, we will see how to construct this type of curves. Okay. Okay. So, by definition or by defining a different sets of axes, the same response spectrum can be transformed into what is known as the PI diagram. Okay. So, with the specific response or damage level defined, okay, if we define the damage level, okay, the points on a PI curve indicates the combination of loads or pressure and the impulse that will cause the specific failure or the damage level. Okay. So, what we need to do here is that here we are saying that the system remains in a perfectly elastic stage. Okay. So, for that we have created a response spectrum. We can create the similar response spectrum for a plastic stage, okay, or for an elastoplastic state. Okay. So, the way we define the damage level, okay, so depending upon the damage level we can define the different response spectrum. Okay. And after that, taking the same response spectrum and representing it on the different axes, okay, we can construct the PI diagram. Okay. So, with a specific response or damage level defined, okay, specific response means elastic, elastoplastic or purely plastic. Okay. So, the different response or the damage level, the points on the PI curve indicate the combination of the load and pressure, okay, that will cause that particular damage level. Okay. So, this curves divide the PI diagram into two distinct regions. Okay. So, the combination of pressure and impulse that fall to the left of and below the curve will not induce the specific damage level. Okay. So, if the system is remaining below this thing, okay, then the damage level will not be achieved. Okay. And if it is right or to the above, okay, that damage level will be exceeded. Okay. So, this is how the PI diagram will be used. Okay. So, as we have seen, it can be broken down into three spheres: quasi static domain, dynamic domain and the impulsive domain. Okay. Okay. So, the analytical solution for a PI diagram. So, what we can also do is that we can obtain a closed form solution of a PI diagram for the idealized structure subjected to a specific load pulse. Okay. And this is accompanied by deriving the response spectrum from its respective responsive functions under force and transient vibration. Okay. So, let us say that we are having an undamped elastic single degree of freedom system subject to a rectangular load pulse with duration Td. Okay. So, if we have this system, okay, and this is my chosen degree of freedom x. Okay. So, then what we can do is that we can draw the free body diagram. Okay. So, using D'Alembert's principle, we have the inertia component. So, this is a fictitious force. Okay. Then we have the stiffness component and we will have the damping component. Okay. And it is on a roller. This is the chosen degree of freedom and this is the equivalent forcing function which is represented out here. Okay. So, if you are writing the free body diagram, so it becomes dot. So, it becomes this is kx, this is x P naught T, and this is our damping component. Okay. Okay. You can write directly by Kx and Cx dot. Okay. So, the equation of motion becomes the initial component plus the stiffness component plus the damping component equals to P naught T for time 0 to Td, okay, because here the load is applied till Td, and after that the system will vibrate due to the final response of the previous forces equals to 0, and this is for Td2 or T greater than Tt. Okay. So, we are taking an undamped system here. So, we are ignoring the damping. So, the damping goes to 0. Okay. So, if the damping goes to 0, then the response of the system is broken down into two parts. Okay. It is represented by the steady state response and the transient response. Okay. So, for the first phase, okay, the response can be written as x t can be written as a cos omega n t plus b sin omega n t plus p by k. Okay. So, this response is 0 t t d, initial condition x equals to 0, x at time t equals to 0 0 and x dot at time t equals to 0 0. Okay. From there we can calculate a b, okay, and if we do all the calculations, then this is the equation of the forcing function when the system is still under the influence of the loading function. Okay. Once the loading function is removed, okay, that is the second equation, then what we need to do is that the second solution will be a1 b1, let us say it to be 2 cos omega n t minus Td plus b2 sin omega n t minus Td. Okay. And then we apply the initial condition where x at t equals to Td is given by x naught, that is the value of this function at this point, and x dot at t equals to Td is given by x dot Td. So, if we put the initial conditions over there, okay, using the end conditions of the previous equations, we will get this equation. Okay. So, this will give us a total response of the system under the dynamic loading, okay, and then we can calculate the differentiate it, and we can calculate the x max 1 and x max 2, and then we can calculate the absolute x max. Okay. So, from here we take the absolute x max, okay, and we can construct our pressure and the impulse diagram from here. Okay. So, just solving the equivalent single degree of freedom system, we can calculate our responses. Okay. So, moving ahead, okay, the structural elements can be represented as equivalent single degree of freedom system by means of load and mass transformation factors. Okay. The total structural response can then be represented by the dynamic equation of motion, the one we were talking just right now, with the sum of an inertial term based on the mass of the structure and the stiffness term based on the structural geometry and the material properties. Okay. So, depending upon the different loading equations, we can represent the load functions. Okay. The blast load will deliver an impulse I to the target structure given by this equation. Okay. This is nothing but the area under the positive phase duration. Okay. Okay. Where I is the area beneath the load function. Okay. So, this area will generate the impulse. Okay. So, in the absence of the damping, the equation of the motion of the structure is this one, okay, as we have seen earlier. Okay. So, if this is my structure, if this is my structure, okay, this is my structure, I can draw the free body diagram of this structure. Okay. Where I am representing my x like this, okay, kx x using D'Alembert's principle, the pseudo acceleration and forcing function t. Okay. This is the equation of motion, okay, of that particular system. Okay. There was damping c(x) dot, but we are ignoring the damping. Okay. So, then the solution to my equation. Okay. So, the solution to the equation of motion, okay, will be in two parts. One will be the part where the load is applied. Okay. So, from 0 t to Td, and the other part where t is greater than Td. Okay. So, the first part will have a1 cos omega n t plus b sin omega n t plus the t over Td by k naught. Okay. And the second part will be when the load is being removed. Okay. So, a2 cos omega n t minus Td plus b2 sin omega n t minus Tt. Okay. So, the first part, the initial condition is that at x equals to, at x t equals to 0, x equals to 0, and velocity at time t equals to 0, it is 0. Okay. And for the second one, the initial condition will be x at t equals to Td, whatever is the value calculated from this point, let us say x naught, and x dot, that is the velocity at t equals to Td, the velocity calculated at this point. Okay. So, if we do that, we will get the solution. Okay. So, here we will get the solution for the x. So, differentiating, we can calculate the x max, okay, and after that we can calculate the absolute x max. Okay. And we can use that equation, okay, we can use that equation to calculate the maximum value of the displacement. Okay. So, this is how we can calculate it. Okay. And this is again what we are saying here. Okay. Differentiating this equation, we can get the x max. Okay. So, using these equations, okay, we can calculate the maximum response, and from the maximum response we can calculate the PI diagram, okay, response of the PI diagram. Okay. Okay. So, we can also consider the relative magnitude of the quantities of T and Td. Okay. So, the case where the positive phase is long compared with the natural period. Okay. So, the load may be considered as remaining constant while the structure attains its maximum deflection. Okay. For this example, there can be a case for a structure loaded from the detonation of to a significant amount of high explosive at long range. Okay. So, the maximum displacement x is then becomes solely a function of the peak blast load F and the stiffness case K. Okay. So, this again boils down to a equivalent quasi-static loading. Okay. The structure is seen to have reached its maximum displacement before the blast load has undergone any significant decay. Okay. So, the structural response. Okay. So, if this is the loading, the structure has already attained its maximum response. Okay. Okay. When the case where the positive phase is short compared with the natural period. Okay. So, this was the impulsive case. The first we are dealing with the quasi-static case. Okay. This was the quasi-static case, this is the impulsive case. So, the load has occurred, it has died down, and then the structure starts to respond. Okay. Then the Td is much smaller than T. Okay. Time duration of the blast loading is much smaller than the frequency of the structure. Okay. The load has finished acting before the structure has time to respond significantly, and most deformation occurs at time greater than Td. Okay. So, this was the impulsive part of the PI diagram. Okay. Then the displacement is a function of the impulse, stiffness and mass. Okay. The response of the stiffness is driven by the impulse. Okay. The external quantity is impulse and the internal quantity is stiffness and mass. Okay. Basically, it becomes dependent upon I and omega n of the structure. Okay. Third case where the positive phase duration and the natural period is similar. Okay. So, this was the dynamic phase, okay, the intermediate phase in the PI diagram. Here time of detonation, okay, or time of the application of the loading and the time period is approximately same or they are comparable. Okay. So, the assessment of the response is more complex, possibly requiring complete solution of the equation of motion of the structure. Okay. So, both things are happening simultaneously and the response is, you can see it is dynamic in nature. Okay. Okay. So, then we can break down the regimes, okay, depending upon the ratio of the both the times, we can break down into regimes. Okay. This are not set in stone, okay, but they are depending upon the response of the structure. Okay. So, using these ratios we can have a idea that whether it is falling in the impulsive regime, dynamic regime or the quasi-static regime. Okay. So, again using this thing, if we can again calculate the time, okay, Tm, that Tm is the time required for the element to reach its maximum response. Okay. So, here also we can have a generic classification. Okay. Again they are not set in stone, all these numbers, and they are just an indicator, okay, of the response that is happening. Okay. So, evaluation of the limits of response. Okay. So, the work done by the load as it causes a displacement x max becomes f x max, okay, f times x max. Okay. The strain energy acquired by the structure is the area beneath the resistance displacement graphs. Okay. So, this is the strain energy of the system. Okay. So, equating the two, okay, we get the representation, okay, and xst is the static displacement, okay, that is denoted by the magnitude of the forcing function and the equivalent stiffness, okay, and this is the xst is the static displacement that would result if the force was applied as a static load. Okay. So, x max is the magnitude of the dynamic load represented as x max, and xxt is the static load. Okay. So, they can lie in the region of 2 to 3. Okay. So, this we can quantify as the dynamic amplification, okay, or we can also call it as the dynamic load factor, okay, and this gives the upper bound of response, okay, and it is called the quasi-static asymptote. Okay. It means that the number by which my static load can be multiplied to give an equivalent dynamic load response function. Okay. So, evaluating the limits of response. Okay. In the impulsive limit, the pulse duration tends to 0, okay, the impulsive limit. Okay. So, the pulse, okay, it tends to be shorter and shorter, and an idealized impulsive load is delivered to a structure which produces an instantaneously velocity change. Okay. The moment is acquired and the structure gains kinetic energy, which is converted into strain energy. So, as it tends to 0, as it becomes shorter and shorter, this can be idealized using an impulsive curve. Okay. This impulse causes an initially stationary structure to acquire a velocity. Okay. So, this is what happens to a structure, and from this the kinetic energy imparted to the system is given by this equation. So, this structure will acquire the same strain energy as before because it is displaced by x max. Okay. And if we equate the kinetic energy and the strain energy, we will get the equation of the impulsive asymptote of the response. Okay. So, this is how the response spectrum is being converted into the PI diagram. Okay. So, moving ahead, then the quasi-static and the impulsive asymptotes are drawn on a response curve of TTD against x max Fk. Okay. So, this is TTD, or it can be also written as omega and TD, okay, and this is the x max function. Okay. The actual response of the structure then can be sketched, and the three regimes of quasi-static, impulse and dynamic response are identified on the resulting graph as regions 1, 2 and 3 respectively. Okay. So, this is the 2 region, 3 region and the 1 region. Okay. Okay. Then the pressure impulse diagram. Now, the equation 3 can be rewritten as in this format. Okay. This is the equation of the modified quasi-static asymptote plotted on the graph with ordinates this one, and if we multiply the f of a figure on the left by the inverse of the ordinate, okay, so we get a non-dimensional impulse. Okay. So, what we are trying to do is that from the response curve we are trying to draw the pressure impulse diagram. Okay. Okay. So, from here to here, okay, multiplying by the terms, okay, the same graph, okay, can be plotted in terms of pressure and impulse. Okay. So, this becomes my impulsive region, dynamic region and my quasi-static region. If it remains below this line, there will be no damage, and if it is above this line, there will be a damage to the structure. Okay. So, from here to here, we are changing from the response graph to the PI graph. Okay. Okay. So, what did this graph is doing? Okay. So, this graph is allowing an easy assessment of a response to a specific load. Okay. Once a maximum displacement or damage level is defined, this curve indicates the combination of the load impulse that will cause failure. So, the failure region can be seen like this: damage failure region, no damage failure region, impulsive region, dynamic region and the quasi-static region. Okay. So, in one go we can categorize the what is happening to the structure, in which region it is falling and whether the damage will occur or not. Okay. So, this becomes a very handy graph. Okay. So, the pressure impulse curves has been derived from a study of house damages by a bomb dropped in the UK. Okay. So, this is a case study where, depending upon the different bombs dropped on a UK is given here. Okay. So, from here we can see what is the response of the structure depending upon the weight of the explosives used and the distance on which the structure is located. Okay. Okay. So, A, the region A, it corresponds to the complete demolition of the building. Obviously, it is lying above this graph. Okay. B means, B is represented by a curve. Okay. So, here B means the damage level is severe. Okay. So, once we are moving from here to here, the damage intensity is increases. Category CB implies the damage rendering the house temporarily uninhabitable. So, these are the different damage categories defined. CA indicates minor damage and D refers to a damage which is significantly low, but it again requires some repair. Okay. So, from here to here we know that this pressure impulse diagram as we increases. Okay. So, as we are in this region the damage is more, in this region the damage is less. Okay. So, here the structure has collapsed and here it requires some significant rehabilitation. Okay. So, we are trying to do a small example. Okay. So, a masonry infill panel is hit by a short triangular positive phase over pulse. Okay, with peak as 250 kPa and duration is 15 millisecond. Okay. So, we need to compute the specific impulse per unit area. So, impulse per unit area is nothing but the area under this curve. Okay. So, we can calculate it. In the next example, a steel column. Okay. And here the first mode natural period is subjected to a blast load. It means that we are considering the first mode response. Okay. So, this response we are considering. Tn of the structure is given, positive phase of the blast loading is given, and we need to identify the blast regime. Okay. So, we calculated the Td over Tn. Okay. And it comes out to be 6.8. So, this is less than 10 and it is likely to follow in the dynamic regime. Okay. So, I will stop here. Please look into the examples and practice it, and we will continue in the next lecture. Thank you.